Good afternoon, everyone, and thank you for listening to my talk. My name is Stephen Pickard. I'm a PhD candidate from the University of Newcastle, Australia. My collaborators for this paper are my supervisor, Dr. Ami Edels from the University of Newcastle, and Dr. Leslie Blaha from the US Air Force Office of Scientific Research, Arlington, Virginia, United States of America. The research is investigating a methodology to detect a loss of situational awareness through the assessment and measurement of cognitive workload using the detection response task. In this talk, I will cover the background of the previous research. I'll briefly describe the model of situational awareness. I'll introduce the experimental approach for this study and describe the major result findings and discuss the implications. And I'll provide an outline of the next steps for the research. The ultimate vision of the outcomes of the research would be to implement systems that use the inbuilt telemetry and recording of aircraft parameters and detection and analysis of pilots' reactions and behaviours to identify when their performance is affected and they are losing or have lost situational awareness. This will potentially allow the timely intervention or support to maintain pilot situational awareness and avoid pilot errors leading to catastrophic outcomes. In a previous study presented at the ISAP 2021, we investigated the theory and existing perceptions of situational awareness through a literature review and survey of current aircraft pilots to get their understanding of situational awareness, how it is taught and assessed. The outcomes of the first study were used to inform the design of this experimentation phase. The literature review identified a number of previous studies related to situational awareness and the connection between situational awareness and cognitive load, where increases in workload led to increases in error and decreases in overall performance, as evidence of a loss of situational awareness. Most of these experiments were conducted in aircraft simulators, many of which the results are inconclusive and highlight the large range of variables involved, such as individual differences, pilot experience, learning effects, that potentially impact on the results, not to mention the cost and resources required to conduct experiments in aircraft simulators using operational pilots. We are trying to pair that back to the essential behaviours that a pilot exhibits and being able to simulate this in a simple and cost-effective way that allows the control of variables and is easily replicable. Though the term situational awareness is commonly used in aviation, transportation, and other critical industries, there is still debate about the most appropriate formal and operational definitions. Situational awareness has a range of definitions, from the simplistic definition of simply knowing what is going on around you to the more complex perceptions of events in elements in time and space. The basis for the current research approach to situational awareness is a three-level model proposed by Micah Ensley from her 1995 paper Towards a Theory of Situational Awareness in Dynamic Systems. The three levels of situational awareness are perception, comprehension, and projection. The approaches to measure workload and situational awareness include the use of physiological, behavioural and subjective measures. We determined based on the positive aspects and critiques of each method, plus the level of available subject matter expertise, to focus on the behavioural cognitive approach, supplemented with some subjective analysis. By implementing contextualised tasks aimed at each of the levels of situational awareness, we hope to better understand the relationship between cognitive workload and the impact against each of the three levels of situational awareness. In the present experimental study, we use a computerized software platform called ModMe, which stands for Modifiable Multitasking Environment, to investigate the effect of cognitive load and task difficulty on performance and possibly on situational awareness. Specifically, we assess cognitive workload and the possible link to situational awareness across the three levels, using a variant of the detection response task. The DRT is embedded in a multitasking interface designed to replicate pilot behaviours, such as the fine and gross motor skills in operating the joystick, visual scanning, and responding to stimuli. The results show the ModMe software provides a valid platform to manipulate and measure cognitive workload in a simulated aviation context and is sensitive to workload manipulations. As such, ModMe, leveraging the DRT, offers an objective way to assess cognitive workload in a lab that could alleviate some of the shortcomings of current subjective methods of workload and situational awareness assessment, such as the NASA TLX and the SART. The study consists of two conditions. The first condition consisted of a basic multitasking experiment with the primary task on the right, the crosshair tracking task, and the secondary task on the left, referred to as a monitor task. Condition 2 had the same primary and secondary tasks as condition 1, with an additional tertiary task called the aircraft coordination task to further increase workload and begin to introduce situational awareness-related reasoning. The design was within subjects such that each participant completed both conditions. Each condition consisted of a 1-minute practice at low difficulty level, followed by 4 1-minute trials with differing difficulty levels, with the order of presentation counterbalanced across participants. Difficulty was manipulated by increasing the jitter rate of the primary crosshair tracking task. Participants completed condition 1 and condition 2 twice. The results were compared across repeated conditions to assess any practice and learning effect, and there was no significant effect on the learning level effect across the 2 conditions. The participants were tested individually in the Newcastle Cognition Lab on standard Dell computers connected with a joystick. The participants were 54 undergraduate students from the University of Newcastle, 36 male and 18 female, ages ranging from 18 to 39 years. 51 participants were right-handed and 3 were left-handed. The setup of the experiment was such that the joystick could be relocated to the left side of the keyboard to accommodate for left-handed participants. The demographic data also included a question related to the participants' gaming habits for the number of hours spent gaming per week. We noted that post-experiment analysis showed the amount of time spent gaming did not correlate with better experiment performance. Participants completed the experiment in about 30 minutes and were awarded course credits as compensation. In condition 1, the primary task on the right of the display is a version of the object tracking task referred to as a crosshair tracking task. The small green circle, the reticle, randomly jitters around the display, and participants used a joystick to manoeuvre the reticle back to the centre of the display. The instructions to participants were to maintain the reticle in the centre of the display. The difficulty manipulation for the experiment was implemented through different jitter rate parameter settings for each of the 4 trials, set respectively at 2, 4, 6, and 8 pixels per screen refresh. The position of the reticle was recorded every 3 milliseconds to allow analysis of the performance of the primary task. The secondary monitoring task on the left followed the standard DRT protocol in accordance with the ISO standard, whereby the green reticle turned red alerted randomly between 1 and 3 seconds, and the participants pressed the F6 key on the keyboard to respond as soon as they detected the alert. The alert reset back to green after 1 second if the participants didn't respond. Response times, hits, misses, and false alarms were recorded. These 2 tasks were designed to exercise the first and second level of situational awareness, detection, and comprehension. Condition 2 consisted of the same primary and secondary tasks with the same parameters as for condition 1, but with the addition of a tertiary task, the aircraft coordination task, to further manipulate the workload and introduce projection-related reasoning. The tertiary task is designed to resemble an aircraft moving map display, exercising in the 3rd stage of situational awareness, where errors and slow response times would potentially indicate a loss of situational awareness. Target aircraft randomly enter the display and track across the display on a potential collision course with the centre aircraft. Participants were instructed to respond by pressing the F7 key as soon as they project that a collision would occur. The task parameters for the target aircraft speed and percentage of collisions were set to be constant across each trial. If the participants correctly determined the aircraft would not collide, they were to withhold response, and this was recorded as a correct rejection. Similar to the monitoring task, we also recorded response times, hits, correct rejections, misses, and false alarms for later analysis with the signal detection theory parameters. The validation of the experiment was conducted through a number of methods. The signal detection theory D' was calculated for the secondary monitor task and the aircraft coordination task, showing good discriminability between the signal and the noise for both tasks. These and other tests showed that the experiment was consistent across conditions, trials, and between participants and ran as designed. 3 participants' results were excluded due to the large error rates and large tracking errors, indicating that they were not following the instructions for the experiment. This figure shows the results for the primary crosshair tracking task. Performance on the primary tracking task was calculated as tracking error, the Euclidean distance between the position of the reticle and centre of the task display, and shown on the left, on the Y column. If the participants are prioritising the instructions to keep the reticle centred and the distance should remain small, the plot shows the mean distance for all participants per difficulty level for both conditions. As the difficulty level increased across trials, the data shows an increase in mean distance. Interestingly, with the inclusion of the tertiary task for condition 2, we do not see an increase in tracking distance values caused by the additional workload. This suggests a consistent prioritisation of resources to the primary task between conditions. This may be due to the nature of the task or that measure of performance is not capturing the participants utilising additional resources. If the participants are using additional resources for the primary task, then the performance of the secondary task would be negatively affected, and we test this in the analysis of the secondary task. Data analysis for the secondary task included calculation of response times, proportion of correct responses across conditions, and participants to determine accuracy and performance for the task, which is a comparison of the response time and accuracy. In the plot, we see the response times on the y-axis for each trial with the increasing difficulty on the x-axis, and a commensurate increase in response times as a measure of increased workload. For condition 2, with the addition of the tertiary task, we see an increase in response times across the difficulty levels. This indicates that participants are utilising additional resources to respond to the tertiary task, impacting performance on the secondary task. This plot shows the response times for correct responses for the aircraft coordination protection task. As the difficulty of the primary task is increased, the response times increase, indicating increased difficulty impacts the speed of projection tasks. For the speed accuracy trade-off, we plotted the mean accuracy and response times per participant and plotted them in the figure on the left and show a negative relationship between speed and accuracy. This indicates that participants did not experience sufficient workload to trade off responding to the secondary task. This plot shows a negative correlation between accuracy, hit rate, and response times, meaning that participants who were more accurate also tended to have faster response times. Conversely, participants who were less accurate tended to have longer response times. This corresponded to poorer efficiency. The figure on the right shows a similar result for the aircraft coordination task, though much less pronounced. We tested performance in a computerised task using the ModMe software where we manipulated load in the number of concurrent tasks and difficulty. Overall performance decreased with increased difficulty as evidenced by the slower response times and lower accuracy. Performance on the primary task was not affected by increased load, having 2 versus 3 concurrent tasks, whereas performance in the secondary task decreased with the increased load. This suggests that as load increases, participants can recruit resources to maintain their primary task performance intact. The recruitment of resources does not come for free, but negatively impacts on the secondary task performance, rendering it slower and less accurate. For the tertiary task, we increase difficulty of the primary task. That pulls more cognitive resources towards the primary, does impact the speed of projection decisions. The number of correct responses for the tertiary task also reduces with the increase of primary task difficulty. According to Jones and Ensley, as task complexity increases, performance will be impacted as participants' limited resources are used, and there will be a drop in performance. This reduction in performance can impact situational awareness, leading to errors and potentially catastrophic consequences. The results of this study demonstrate that the contextualised DRT is sensitive to both difficulty between trials and increased workload between conditions. The primary and secondary tasks reflect cognitive load in the first and second stages of Ensley's situational awareness model for perception and comprehension, and the tertiary task reflects workload impacts in the third stage, the projection. Using an appropriately designed experiment, integrating the DRT and the aviation contextualised tasks, aspects of situational awareness across the 3 levels can potentially be assessed and measured in real time. Further analysis of the data will be undertaken to understand the capacity ratio of the tasks and identifying strategies for optimal task performance. The future direction of the research is to develop strategies for improving resilience to a loss of situational awareness. Further investigations may include the use of physiological measures such as eye tracking to see how they would add value to the understanding of situational awareness and cognitive workload. Thank you, and I'll open up to any questions.